Financial Modeling, Topic 9, Section 2. Use duration to measure the sensitivity of bond prices with respect to changes in interest rates. So in the first topic, we said that the value of a bond, V, is the present value of expected cash flows discounted at some rate, R. Now you'll notice from this formula there's going to be an inverse relationship between bond value and R. As the discount goes up, the present value of cash flows goes down. Now long-term bonds are going to be more sensitive to changes in interest rates. You can just think about if this is to the 1, 2, 3, or 10th power, the longer that term, the bigger effect that R is going to have on the value of the bond. So long-term bonds are more sensitive to changes in yield. A measure of the sensitivity is a measure called duration. Now, duration is a measure of both the average cash flow timing, in other words, kind of the maturity of the bond, and the interest rate risk of the bond. There are several duration measures which we're going to cover. In this topic, we're going to cover Macaulay and modified duration, and then later we'll talk about effective duration. So Macaulay duration is a measure of the average maturity of the stream of payments associated with a bond. Specifically, it's the weighted average length of time until the bond's remaining payments are made, with the weights equal to the present value of each cash flow relative to the present value of all cash flows. We can write that as the sum from I equal 1 to T times F, right? That is counting all our periods. And what we're going to do is take the present value of each cash flow at period I, divided by the total value of all cash flows. So basically that then becomes a fraction of the value in period I of the total value, and multiply that times I divided by F. So we're going to sum up those values. And what this turns out to be is the weighted average time period to the cash flows. So let's go ahead and to our spreadsheet. We'll do that. And then later we'll calculate modified duration. Modified duration is going to be our Macaulay duration over 1 plus R to the F, kind of like the present value of the Macaulay duration. So we'll go to our spreadsheet. And we'll do it for this bond 2, which is this 5-year, 2 payment per year, 10% annual coupon rate bond. That bond's present value of cash flows is $1,039.56. And then we'll do a calculation here. I'm going to take the present value of the first cash flow divided by V, the value of all the cash flows, times the period divided by the frequency. So basically, I'm just going to weight the periods by the fraction of the value received. I'll copy this down. Whoops, got to anchor something, got to anchor the frequency, F6. Again, I'll copy that down. So it's the periods times the fraction of value. I will sum that up. And 4.07. So that is the average timing of the cash flows. In other words, the biggest cash flow does happen 5 years from now, which is 10 6-month periods. However, you're getting a little bit of money every 6 months. On average, in present value terms, on average, you get your money back in 4.07 years. Think of it as most of the weight is right here 5 years from now, but each one of these periods has a little bit of weight. So on average, you get your money back in 4.07 years. That's why the Macaulay duration is often quoted as years. The duration is 4.07 years. Now the modified duration is simply the Macaulay duration over 1 plus my discount rate divided by the frequency. So it's kind of like the present value of the Macaulay duration. That's 3.899 years. So you have Macaulay duration, which is the weighted average time period of getting your money, and the modified duration, which is the Macaulay divided by 1 plus R to the frequency. Now here's a function that calculates the modified duration. Let's look at this function right here. Well, I've got that little extra character in there again. If I have my bond val in my module, I can then use this function called modder. Now notice the first thing this function does, it calculates V by calling on bond val. Notice that bond val and modified duration functions use the same parameters. So the first thing modder is going to do is it's going to value the bond to get the V. Then it's going to calculate the total number of payments. Then it's going to do a loop. That loop is calculating the weighted average time period, where each weight is simply the weight of the coupons divided by the total value of the bond. The last step is we handle the par payment by taking the last par payment, taking the present value of it, divided by V, and multiply times that final period. So now, basically at this point, the function is the Macaulay duration. The last step is it takes that value from the last step and divide by 1 plus R over the frequency. And that converts from Macaulay to modified duration. So we can take our function, which is already in our worksheet. Notice I have modder right here. And then I will insert it here just to show I get the same value. So I'm going to delete this out, insert a function, look for modder, and go ahead and put my parameters in. Coupon, par, maturity, frequency, R. And there's my 3.899 years of modified duration. Now let's talk a little bit about modified duration. Modified duration is the Macaulay duration over 1 plus R to the F. Now it could be shown that the modified duration is equal to minus the slope of that price yield function divided by the price. In other words, if I were to graph a price yield function of a normal bond, I'm going to get an inverse relationship between price and yield. If I were to look at the slope at the current price and yield, if I take the minus of that slope and divide by the value of the bond, that is going to give me the modified duration. So you can think of modified duration as the slope of the price-yield relationship, the value-yield relationship of a bond. But it's not exactly that because, one, it changes its sign, and two, it divides by V, so it makes it a percentage. So one way of another interpretation, if I take this formula that my modified duration is minus dV dy, let's call this V, the value of the bond. Let's call this Y, the yield to maturity or the discount rate of the bond. This is the slope. I'm going to take the negative of it and divide by V. So it kind of puts that slope in percentage terms and makes it a positive number. So rearranging this, I can say the change in the value of a bond is minus its duration times the change in yield times the initial bond value. Or if you want the change in value of a bond as a percentage, dV over V, you can take just minus the duration times the change in yield. So this gives us another interpretation of modified duration. Modified duration is the measure of a slope of the bond's value-yield relationship. So the higher the duration, the more sensitive the bond is to yield changes. It's also related to the average cash flow, kind of like the Macaulay duration concept. However, once you calculate modified duration, there's a very specific interpretation of that number. That number tells you the percentage change in price for 100 basis point change in rates. So again, back to this bond here, it had a modified duration of 3.899. What that tells me, if interest rates are up 100 basis points, 1 percentage point, the discount rate is up 100 basis points, I am going to lose 3.89% of the bond's value. And if rates are down 100 basis points, I will gain 3.89% of the bond's value. So let's do a little exercise. Let's look at a 30-year bond. And this 30-year bond has a coupon of 10, discount rate of 9, which we'll also call our YTM. We'll assume the bond is trading at its present value of cash flows. has a par of 1,000, maturity 30 years, frequency twice a year, and it's selling for 1103.19. So what we're going to do is go to the spreadsheet, and I'm going to see how the bond value changes as my discount rate goes from 9 down to 6 and then 9 up to 12. In other words, plus or minus 300 basis points. And then I'm going to use my duration to estimate the value changes. I'm then going to figure out, using the duration, try to estimate the value of the bond. Rates are plus or minus 300 basis points. Then I'll actually value the bond using bond val, and then we'll compare the results. So I'm going to go to the spreadsheet. Let's go to sheet 2. And the first thing I want to do is we're going to calculate the value change of the bond if rates are down 300 basis points. Again, I'm going to use my formula. DV is minus the modified duration times change in yield times initial bond value. So what I'm going to do is minus modified duration. I've calculated modified duration for this bond at 10 years. Again, this is a 30-year bond, has a modified duration of 10 years. I'm going to anchor that. So minus duration times change in yield times initial bond value. I'll anchor the initial bond value. So if rates are down 300 basis points, this bond is going to gain about 30%. Modified duration of 10 times 300 basis points, so it's going to gain about $337. I'll copy that down. If rates are if rates are up 300 basis points, it'll lose 337 basis points. That's our inverse relationship. Now, if I take that change in value and add the initial bond value, I estimate that the bond value, if rates are down 300 basis points, will be $14.40. I'll copy that down. And what you see here is a bond price yield relationship using duration as our estimator. So here's our inverse relationship. The slope of this line is going to be that 10 or minus 10 as a percent. However, I'm going to do one more thing. I want to value the bond. All right, this is an approximation of the bond's value using the slope, the modified duration. Let's go ahead and value the bond. Let's go ahead and insert bond val. And let's go ahead and put in the annual coupon rate, 10%, anchor it. Par, 1,000, anchor it. Maturity, 30 years, anchor it. Frequency, 2, anchor it. Now it says discount rate. Let's let the discount rate vary from 6 to 12. So I'm actually valuing the bond using this discount rate. So I copy that down, and what you see is the actual price yield relationship appears to be a convex function, right? Bows away from the origin, and it's an inverse relationship. So this is the actual price yield relationship of the bond. Now if I just look at the pricing errors, you'll notice that the duration price is always too low. The actual bond value is actually higher for different rates, varying from 9%. So if we calculate those errors of taking the duration price minus the actual price, or the duration estimated price minus the actual price, we have these errors. And what we call these errors are convexity errors or curvature errors. They're errors due to the fact that the actual price yield relationship of a bond tends to be convex. Any linear estimate of value changes using a first order derivative, a slope, is always going to estimate along a straight line. So what you have here are these pricing errors, are the distances between the actual price yield relationship in orange and the duration estimated value in blue. However, it does give you a handy way of calculating a quick value change. If someone told me I had a bond with a duration of 10 and rates are down 300 basis points, I'm going to guess a 30% increase in price. So I'm going to guess about $300 and some increase. So it is a handy way of estimating price. So in this topic, we use duration to estimate the measure to estimate the sensitivity of bond prices with respect to changes in interest rates. In the next topic, we'll talk more about the convexity.